I will be providing you some good homework 3 hints along the way today if you're listening carefully. Homework 3, of course, is not due tomorrow night. We extended it 1 day just because today we are finishing the material. So you should be able to complete any of the questions after today. And that means we extended it till Thursday night. There will not be a homework 4 due next week. Next week you're studying for that exam. Next week you are doing the review problems that go up for either the Sunday review. There will be review problems that I'm going to have that will cover Tuesday and Thursday in lecture. Not the full lecture. There's always some new, but I always promise some review. So we'll have some review next week. And in labs next week also will be some review. The exam is, of course, Thursday night, a week from Thursday, next week. I have details on the next slide. Some have asked about the Sunday review. My questions for that review will go up probably tomorrow afternoon. And I'm asking you to bring a copy of them with you. The best thing would be if you're coming to try out the questions or at least read them through. If you cannot attend on Sunday, we will be capturing it, the slides, everything that's written, and the audio, so you can watch it on your own if you'd like through the iTunes U. The key page number is 93 for material ending, and of course your first 3 homeworks. Anything correspondingly in labs that you've covered. When you come to the rooms, you're going to have alternate seating. It's best if you don't bring anything except your calculator, your ID, pens and pencils to write with. But the less you bring, the better, because you're going to be asked to put them along the front wall or the side wall, just to make it easier to get in and out of the rows. All right. And I have a couple clicker questions at the start and a couple in the middle, so we will be doing that shortly. Let's just get back into what we're studying here and giving you a homework 3 hint along the way. Someone tell me, what is P? What does P represent? What's another word for P? Population proportion. Another word that could be used to represent P. If it's a population proportion, it's a parameter. P goes with population proportion. Since it is a population numerical summary, it's a parameter. All right, what is P hat? P hat goes with, hey guys, this is for homework problem 6A. Giving it away if you're listening. P hat, the symbol of the hat means it's an estimate. So it is the, not population proportion, but sample proportion. Comes from your data. And since it's calculated on your sample, it's also known as a statistic. All right? P hat goes with sample proportion and statistic. P goes with population proportion and parameter. Those 3 things go together respectively for sample versus population. You have to decide in that question on the homework whether the number that's there is of one type or the other. And of course those 3 things go together once you determine if it's from the sample or from the population. We are doing, on your homework 3, confidence intervals for P and hypothesis testing for values of P. We test theories about that population proportion. We make a confidence interval for P, not for P hat. We make a confidence interval for P, the true proportion, by taking the data and calculating P hat. P hat, your sample proportion, is always in your interval. 100% of the time it's in your interval because it's the center. And you go plus or minus your margin of error to make your interval estimate for values that are reasonable for the true proportion P. Hypothesis testing, which we started last Thursday. Testing theories about what that value of that population rate might be. Is it possible we have a majority in our population? Could it be that the true value P is really greater than 50%? Testing if we have a majority in our population. So when we wrote out H0 and HA together last week, and we'll be doing that again, we always put in the population value because that's what your testing theory is about. All right. On page 83, we have the 5 steps for testing theories. Let's just recap those 5 basic steps. And then I have a little activity to do to help us understand better what a p-value is. Step number 1 is to state the theories. They're sometimes called hypotheses. They were represented by what? H0 or H null, H0 and HA. And we put a statement after that. Now we could write those statements out in words, but it takes a long time then to write them out in words, especially when you're repeating the same thing except for either the true proportion of all people who would vote for this candidate is equal to 50%. The true proportion of all people who would vote for that candidate is greater than 50%. You'd be writing it twice. So we use the notation P. We identify the parameter P as being that population rate and then just write it in terms of that value P. Now, what is always an H naught? H naught always has the equal sign. In fact, you can always write your H naught as P equals and you put your null value there. It is the alternative HA that's going to always have your direction for what theory you want to put to the test. Is it greater than a majority, more than 0.5? Is it less than 0.5 to say you have a minority? Is it changed, different from some value that's specified? The 3 different directions can go in the HA. And it is the direction that you have in HA that dictates how we're going to shade the picture that represents our p-value. And for us today, the couple examples we'll recap and go through, we're going to have a normal curve to represent that model that we find the p-value under, because it's a z-test statistic that we'll be calculating. Step number 2 is always checking if you can do the test. Once you stated the theories, and you now look at your data and say, based on my data, does it look like all my conditions are met? And if so, then go ahead and start doing the test, calculating the test statistic. Now, a statistic you just told me a minute ago was p hat. And of course, that's something you would calculate on your data naturally because you're trying to learn about the true value p, so let's look at p hat. But then we standardize that p hat into a z-score because that's on a frame of reference that we all can identify better with. We know the normal 0-1 distribution better than we know the model for p hat every time you have a different value of p in a different sample size. So we calculate a test statistic. Then we have to find this thing called a p-value. The p-value is going to be a probability, and we'll talk about that in more detail to make sure we understand what that is. The p-value is used to decide if we're statistically significant. The p-value is used to decide, do we stay with H naught or do we reject H naught and go with that new theory? And then, of course, once you've made that decision of which theory your data best supports, then you write up a conclusion in words. And that should be in the context of the problem. Usually going back to what it said you wanted to test in the top part and just pulling that sentence out and using it again. So let's get an idea of what this p-value really is. And for that, we have a little handwriting activity to do. So that sheet that's open on the page before, 82, you want to use that spot. I'm going to ask you in a moment, not yet, we're going to see how long it takes you to print your first and last name. So I'm going to give you all the go. I'm going to ask you to just print your first and last name, and we'll record how much time it takes. I'll have the seconds go by up front. So as soon as you're done, look up front and record your time. Okay? So handwriting activity, printing your first and last name. Ready? Go. Some of you have very short names. All right, everybody's done. You got your first data point observation. All right, you're going to do it one more time with your opposite hand. Switch hands as neatly as you can, first and last name. Let's see how long it takes you now. Ready, set, go. All right. So what I really want is you to work out the difference. I mean, we just did a paired analysis in some sense. We just collected paired data, which we'll be analyzing later as a technique. You have two observations on the same person. Calculate how much longer did it take you to print your name with your opposite hand. That's the value I really want, the difference. And I'd like you to click in what your value was, so I can get a quick look at that distribution to some extent. Normally I might have you gather data from just those around you, but we can gather all the data and take a peek at that distribution a little bit. So how much longer did it take you to print your name with your opposite hand? Let's see how the numbers are coming in. All right, let's have all the data in so we can use this data to make a decision. Last call, 5, 4, 3, 2, 1. All right, stop. So here's our model to some extent. I had to break it up into some intervals, but it is a quantitative response. Here's the axes of 0 to 1, 2 to 3, 4 to 5, and 8 or more. All right, so looking at those values, the data we've collected, I'm going to ask you in a moment to decide between a theory, a null hypothesis, and then corresponding alternative, and decide whether you would stay with this null theory or reject it based on this data. And the theory will be based on what we think the average is, okay? So my theory that I want to have as my null hypothesis is that on average, it takes 3 seconds longer to print your name with the opposite hand. 3 seconds. So you're going to click in whether you're going to support this theory or refute it, reject it. Come on. And tell me what your decision would be based on what you saw, based on what you got, and maybe from those around you. We use data to make a decision. This is the null theory. Would you support this theory or would you refute it? And most observations are in. What are you deciding? Quite a number of you would like to reject H0. There's still a few of you who support it. Now, were there people out there that had 3s? Yes? Even less than 3? We saw it on the histogram of the distribution. Even with the value of 3 being in our data set, even with the variability that we were seeing in our data, we overwhelmingly want to reject H0. What you informally calculated in your head when you said reject H0 is this thing called the p-value. We saw the data and we said, boy, if the mean is really 3, that data doesn't look like it matches that theory at all. We compared the data to H0. The data was not compatible with the average being 3. It was more compatible with the average being greater than 3. The p-value measures how compatible your data is with the null theory. It measures how likely is your data under the null. It's actually how likely or more extreme, but that sense, that idea. How compatible is my data? If the p-value is small, then it says your data is very unusual, not likely under that null. It wouldn't occur very often that null hypotheses were true. It would be unusual, and that's what we saw. Data that came in that was not compatible with that null theory, so we rejected that null theory. The universal rule for every single hypothesis test we do, whether it's the z-test today or the binomial test we'll do today, or whether it's some t-test or chi-square test later, this rule is always followed. You take the data, you compare it to some null theory, you calculate this thing called a p-value, which puts it on the 0 to 1 scale of probability, and then if the p-value is small, it's saying your data would be very unlikely under that null theory, so we will reject it. The p-value is small, reject the null. How small? Do you remember the rule we talked about last time at the end? This is the formal rule. The p-value is small enough. How small? Less than or equal to some cutoff value, which we call alpha, which has the name significance level. And the pocket alpha, the alpha that you should use if it's not specified in a problem, is 5%. That's a very common level. It matches with the most common confidence level of 95%. The p-value is small. It says, seeing what you got under the null theory, hardly ever going to happen. Not likely. So I will reject that theory. It's much more likely to see it under the alternative then, rather than the null. All right. This is the universal rule. Let's turn, this is going to help you right here with question 7 on your homework. Short, simple question. Everyone should get it right. All right, page 84 at the bottom, no, 85 at the bottom. Here are the two possibilities that come out when you're doing a hypothesis test. Two nice bullets that put the three things that go together. Just like there were three things, P, population proportion parameter, or P hat, sample proportion statistic. Three things go together in the testing. If the p-value is small, that leads us to make the decision of rejecting that null hypothesis, and then we get to report the results were statistically significant. The data was strong enough to support the alternative theory and go against the null. Or the p-value turns out to be big relative to alpha. We fail to reject H0. We cannot refute H0. And then we're not statistically significant. Those three things go together. So if the p-value is small, we know that we're statistically significant. If we rejected H0, we know the p-value must have been small. Those three things go together. After you make that decision and identify whether you have significant results or not, you then write out a conclusion in the real world context about the problem. So we went through on page 87 the left-handed artist problem. And I believe that's kind of where we finished class last Thursday. There was this rate of 10% that supposedly applies to the population in general for left-handedness. A theory of artists being more likely to be left-handed. Do the hypotheses make sense in this case? HA is the researcher's claim that it's more likely to be left-handed. We're studying the population of all artists. The sample came in at 150 artists. 18, or 12%, being left-handed. Now, I have a note next to here that your question 8 on your homework 3 could be followed along fairly well by just looking over this complete problem. And we're going to do one more, but this is a one-sided test to the right. And your question 8 is a one-sided test to the right. A different scenario, different hypotheses being put up there, but the same idea. So question 8. Question 8 has A through H. A through G is this page. It's just broken up into even more than 5 steps. One of the parts says, check the data conditions. And we did that in step 2. There's 2 bullets there. A next part says, calculate the test statistic. And we did that as part of step 2. So all of those steps are laid out there in even a little bit more baby step detail. So we had 18 out of 150, or 12% being left-handed in the sample. Well, it looks like we have some evidence to support the alternative theory, that it's higher than 10%. But is it enough, is what we were trying to establish. We could take that 12% and compare it to 10%, and we could draw the model, the bell curve, for p hat. You're asked to do that on the first homework question. What's the model or distribution for p hat for a sample proportion? What kind of values could you expect to see? You got 12% this time, but if H0 is true and 10% is the real rate, what kind of model would you see? But you'd have to draw that whole curve out, put it at 10%, figure out that standard deviation. And instead, we take it right to the z-scale. So we actually are comparing it to 10%. Here is the standard deviation under the null. And we standardize that 12% to see how far away from H0 we are. Your z statistic measures how far away is your sample proportion from the null value in what kind of units? In standard deviation units. 0.82 means the sample proportion was 0.82 standard deviations above that null value of 10%, above 10%, which is above, but not that far away from 10%. And then we said, since different tests are going to have different test statistics that are appropriate, some will be z's, some will be t's, and others, and they have a different model, we need to go to that model for your test statistic and convert it to this probability, the standard universal probability called the p-value. So when you think of a z and you calculate a z, what table do you expect to go to? Table A1, which is a table for what kind of model? A particular normal curve, though. Which one? It's the normal curve that's centered at 0. Standard deviation of 1, the standard normal. You're asked in one of your homework questions to draw the picture of the distribution of your test statistic, z, if h0 is true. If h0 is true, then we've subtracted the right thing. We've divided by the correct standard deviation. We've got a standard normal distribution we can work with. So here is the picture of the model for your test statistic z if h0 is true. And the model here is a standard normal, normal 0, 1. That big N represents a normal model or bell curve. It does not represent the sample size, which I had some students confused about. There's the model under h0 for what you should get for z. And what did we get? Let's put on that axis what we got. 0.82. The p-value is the probability, assuming h0 is true, using this model, of getting what you did get for your statistic, 0.82, or something more extreme. Because I can't calculate just the chance of what I got, because what's the probability of seeing 0.82 under this curve, being exactly equal to that value? There's no area, there's no width. So you do as extreme or even more extreme to measure the amount of evidence. As extreme or more extreme, and that's where your HA plays a role. As extreme or more extreme would be as large or larger in this case. And that, in a picture, is your p-value. And you can find that area. Area corresponds to proportion or probability. Here, area is the p-value. And you did find it with me last time. We looked at 0.82 in table A1. It gave you area to the left, because that's how the table's set up. And we used that to find this area. We found the p-value to be how much? It's kind of big, wasn't it? 26.1, almost 21%. So we saw, well, what we got is not that unusual under h0. What we got or more extreme would happen more than 20% of the time if h0 is true. That's fairly compatible with h0. Not unusual enough for me to reject, because how unusual did it need to be? Less than or equal to what level of significance? Less than or equal to 5%. Then it's really unusual enough to say, go away from h0. So we failed to reject h0. That's how we write it. We don't really say accept h0. We can't refute h0. We don't have enough evidence to go against it. We didn't get 10%, but we weren't far enough away from 10% to say it's not, and it's greater than 10%. We failed to reject h0. We're not statistically significant, and we wrote out our conclusion. That's a good one to follow for your homework problem 8. Now at the top of page 88, it shows you how different amounts of evidence lead to different p-values. I hope it's obvious that if you were testing for being greater than 10% and you took your data and only 8% of your sampled artists were left-handed, that's not even bigger than 10% at all, that you don't even really have to go further. That there's no way you're going to reject h0 in that case. If you calculate the p-value for a proportion p-hat like 0.08, you get a huge p-value, because if you think of the curve that we just drew, you're not even going to have a positive z. You're going to have a negative z. And you're calculating the area to the right of a negative z. Is that going to be a big p-value? More than half. All right. We went to 12%, which is what we actually did get. And we got a test statistic and a p-value, which led us to not rejecting H0. It wasn't enough evidence. But if you had a few more left-handed artists in your sample, out of the 150, if your p-hat was 16%, your z-statistic would now be 2.5 almost. 16% is a little bigger, and now that's a lot more evidence. Your p-value is much smaller. Small enough now to make what decision? Reject H0. If your p-value is small, how small? Less than or equal to your alpha, you reject H0. You go further and further out, and the amount of evidence even gets larger and larger. Part of the reason to show you this is that look at what you can get for z's. You can get a z of 3.7. You can get a z of 7.8. You can get a z of 4 point something on your homework. And whatever z you get corresponds to p-value. The further out, the tinier that area. The further out, the more incompatible with H0 you look. And in each of these cases, we are going to reject H0. The stronger the evidence. So in other words, you have to decide or pick alpha up front. Draw the line and say, as soon as the data crosses that line, I'll reject. You can't look at the data. Oh, if I pick 0.01 versus 0.05, I might make a different decision. Can't pick the alpha after you've looked at the data. Questions? Yes? Yeah. The further out from p-hat from 10% you are, the more evidence you have. More evidence means smaller p-value. More evidence against H0. Do you see the nice pictures in the middle of that page? This shows you the idea of what kind of picture your p-value should look like depending on your direction. We did the middle one, a greater than, and we had an area to the right. If you're doing a lower-tailed test, you always shade wherever you get and go to the left. If you're doing a two-sided, well then you're going to get on one side or the other, but you didn't know which side you were going to be on beforehand, and each side is equally as extreme, so you got to do both sides. Let's try one of those. This is the households with no children example. We used this as an setting up the step 1 together last week. The idea was 48% of households suppose we have no children according to the census. So that's the status quo, the prevailing viewpoint for the true proportion of households with no children. We would like to use a current today's sample of 500 households to see if that rate has changed. We want to use what level of significance? Not 5% this time, but we're going to use 10%. That's your alpha. The 48% is the status quo, the prevailing viewpoint. The different from 48% is because we're looking to see if the proportion has changed. Not is it bigger or is it less. I'm not going to use the fact that 220 out of 500 is less and make it a one-sided test. I want to know if things have changed, and here's the evidence coming in. It's a two-sided test. Step number 2 is asking you to state and verify those conditions. Here's the stating of them. The data is assumed to be a random sample. Did it say we had a random sample of households? And generally you have to have that be stated to you so you can use that data. That was given in the problem. Do we have a large enough sample size? It's not the sample size n that has to be more than 10. It's the sample size times that null rate. Under H0, would I expect at least 10 yeses and at least 10 nos under H0? So my sample size is 500. That looks big. And my null value, the status quo rate, should be 48%. And is about half of 500 going to be large enough? Certainly. We have 240 and 260. And both of these are well above the 10 minimum requirement. You really only have to check the minimum of those two, the one that's smaller. You can always put both of them down. But this is stating and this is verifying. And that's what you're asked to do on your homework. So we can do our z-test. Let's calculate our p-hat. What was our p-hat here? 220 out of 500, and that's a rate of 0.44. I'm testing is the true rate 48% or not. My sample comes in and I get a p-hat of 44%. Why don't I just reject H0 right now? 44 is not 48. Because this 44% was based on a sample. And sample statistics like this p-hat are going to vary from one sample to the next. And I might get 48% next time. I might get 47%. It's going to vary. I have to establish, with knowing the expected variability in a statistic like this, is 44 and 48 really different? So that's why we calculate this test statistic that measures that distance. How far away is the 44 from the 48? Let's look at that distance of 4 percentage points in the right average distance yardstick, the standard deviation. We put the 48 down here. This is the true standard deviation under H0. Now on an exam I would probably calculate top and bottom and put those numbers there just so I could see each part, because if your answer at the end is no work behind it and it's wrong, I can't give you any credit. If your answer is wrong because of the denominator being off, you forgot the square root or something, then I can give you partial credit for it and grade accordingly from there on out. It is a negative. You get about a negative 1.79. So 44% is about 1.8 standard deviations below that status quo value. That's further away from H0 than our last example. Is it far enough away now to say reject H0? What's the next step we have to do? We've got the Z statistic. It looks a little unusual. Let's quantify how unusual with that p-value. So let's draw the p-value. Step number 3, top of the next page. Every statistic you have for doing a test has a model or distribution under the H0 being true. And what's nice is a Z statistic has that natural model you would think for a Z, the standard normal. This is the H0 model for your test statistic. You're asked specifically for that in one of your questions. Now you go to that model and you put on there your data. What was our observed test statistic value? Negative 1.79. And you calculate the chance of getting that or something more extreme. For the more extreme, you look at your HA to see what direction of extreme you're looking for. And it was two-sided. Since it was a two-sided test, both the large and small values are extreme. Being 1.79 below is just as extreme as being 1.79 standard deviations above the status quo. These are equally as extreme, and more extreme would be the tails. These two areas together form my p-value. I need to find both of those areas, add them up to get my p-value. Now those two areas happen to be, though, the same, because it's symmetry. And which area is going to be the easier one to quickly look up on your table? Because it's to the left. So look up negative 1.79 to get that particular half of my p-value from your table. Page 56 in your lecture notes if you don't have your actual table with you. Negative 1.79. What do you get? 0.367? So how do I get the p-value? Double it. Add it to itself. 0.0734. Were you able to find that? Two-sided test. There's my p-value. Step 4 is to click in your answer. We've gone over now this universal rule. I think it was page 85 at the bottom that has the 2 bullets of what can happen. So you can all answer this one correct. Your p-value is 0.07. Our significance level was 10%. My question is, are the results statistically significant at a 10% level? Yes or no? Very good hint. Page 85 at the bottom. I'm asking you, are you statistically significant at a 10%? Or I could have asked you, would you reject H0? Or I could have asked you, listen carefully, is the p-value less than or equal to 10%? All three questions are equivalent. It's a little better. All right. Results are not everyone getting that answer. If you get this rule backwards, you get a lot wrong on many exam questions. Not so much for exam 1 because we have only done this once, but on exam 2 and exam for the final, lots of testing. The p-value is small, you reject the null, and you are statistically significant. We're asking you, is the p-value less than or equal to alpha? 0.07 and 10%. Yes, it is. We would reject H0. So let's write out our conclusion for step 5. But note here, what if I had picked 5%? Would I be significant then at a 5% level? Can you see why you have to decide that line of where if you cross, you reject ahead of time? You can't use your data to say, ooh, if I pick 5%, I can reject, so now let's do the test, and I'll end up rejecting. You pick alpha, the required amount of evidence you need to be convinced up front. Our conclusion would be what? So it either is we have enough evidence to support our alternative theory, or we don't. We do get to reject H0 here. So there is sufficient evidence. To say what? The population proportion of all households today with no children has changed from the census value. To say the population proportion of all households today with no children has changed from the census value of 48%. Now that's what we tested, and this is our conclusion. It would, of course, be very helpful to any reader of this study to include what p hat was, 44%, and to maybe even make a confidence interval around that so they can get an idea of how did it change. But we were testing whether or not it changed. We go back to the problem at hand. We are talking about a conclusion about the population rate and how it's decided its value, whether it's different, greater than, or less than. All right, very good. Another full example, two-sided test also now conducted. Two good examples of a z-test to look at for question 8 on your homework. What happens if we get to a problem like question 9 on your homework, where the sample size is not large enough? What if your sample size is not large enough so that you get that at least 10 rule working for you? What if instead of having, what was your sample size, 50 patients in number 8? You had 50 patients in question 8, and that ends up being large enough, so you can do your z-test. Question 9 says, suppose you actually want to do the same test, but you only have 5 randomly selected patients. If you only have 5 patients, you can't do a z-test. You still want to learn about the population rate. You have a sample that's randomly selected, but the sample size is too small. So you can't get to the normal stuff that you need to do a z-test. Well, we went from the binomial to the normal when the sample size is large. So if the sample size is not large enough, you go back to the binomial and you use that exact model. We're going to use this binomial distribution then, and this is what you have at the bottom of your first page of your yellow card. So I'm not expecting you to memorize this formula at all, only to use it when you need to. And your second box, the bottom of that page, gives you the summary for the small sample binomial test versus what we just went through earlier, the large sample z-test, both for learning about a proportion. You will not state the hypotheses any differently. Step 1's the same. Step 2 is the check, do I have a large enough sample size? And you might say, oh, I don't. So you end up going to a different route and doing a binomial test. A binomial test is kind of opposite of the z-test. The z-test we just did, it took a bit of work to get that z-statistic worked out. But once we got the z-statistic, we went to table A1 and found the p-value pretty easily. In the binomial test, the test statistic is the easy thing. The test statistic is your count statistic. Tell me how many in my sample said yes. How many in my sample responded? How many in my sample said yes? The number of successes in my sample. The model for that test statistic is the binomial. So I have to use this binomial model that works under H0 to compute the p-value. So that means I've got to use that n choose k formula to work out the p-value. That takes more work. So let's try it out. In this example, we have 10 subjects, all given a treatment, and 9 of them improve. Nine out of 10 is 90%. That looks pretty good. I simply want to put to the test, can I say I have a majority that improve? Do that at a 5% level of significance. So can you write out the hypotheses? I've already identified for you the parameter, the population proportion of all people who improve with this treatment. So what will be H0 and HA? I would like to support my theory, which is that I have a majority. That goes in HA. And how would I represent a majority again? P is greater than half. More than 50% would be a majority. H0 will be that we don't have a majority. H0 will always be where I should put the equal, and I can leave it with just the equal. Or I could write that and no points off if it's written as less than or equal to for H0, because you're testing majority versus not. But all I'm going to do is compare my data to the 50% rate and not to the 40 or something that's less. I don't need to do those if I show I'm bigger than 50%. So the equal is an H0. What helps then is this identifies the null value for that rate that you use in doing your test. All right, there's the theories. It's a one-sided test to the right again. The test statistic is easy. My test statistic is not a z. My test statistic is not p hat, but it's simply the count. How many in my sample of 10 subjects improved? 9. My test statistic x, the count statistic, is 9. It's going to be given to you in the problem as they report the results of the study. So that's not hard. You don't even have to really compute it. You just report it. But you do have to compute this p-value. All right, so the p-value is no longer going to be a normal curve because I don't have a large enough sample size. By definition, the p-value is the probability of getting a test statistic as extreme or more extreme than the one you got. A test statistic here is x, and I need as extreme or more extreme than what I got, which was 9. So that's what? Greater than or equal to 9. And what's the last part that makes the definition of a p-value correct? You find this probability assuming H0 is true. Assuming, and what does H0 say? Assuming p is really 0.5. So that gives you the value of p to use to find that p-value. So what's as extreme or more extreme? Either 9 or what's more extreme than 9, improving out of 10? All 10. Find the chance of 9 and find the chance of all 10. Here's a couple of binomial probabilities we need to work out then. Out of the 10, pick 9 that improve, and the success rate is 0.5. If the success rate's 0.5, what's the failure rate? 0.5. And there's one of those. And for the other part, getting all 10 out of 10, it's 10 choose 10, 0.5 to the 10th. The failure rate applies to no one. It's very easy in a binomial problem to not do the more extreme part, because here you can calculate the chance of getting as extreme. There is a probability at this point 9, but not then following the basic definition of a p-value. You have to have the definition of p-value be the same, so it's always as extreme or more extreme. All right, what's 10 choose 10? How many ways to take all 10 friends to the dinner? One way. And what's 10 choose 9? You're picking the one way to leave that one person at home, or the 10 ways to leave that one person at home, so 10. And then you've got the 0.5, you raise that to powers. And you should get a number between 0 and 1, a p-value of 0.107. So try checking that out sometime, that you get the same answer. There's our p-value. Somewhat small, 0.0107. If h0 were true, and the rate were just 50-50, the chance of seeing what we got, 9 out of 10 improving or more extreme, would rarely happen. Only about 1% of the time would you see that kind of result. Is our data compatible with h0? That's how likely it is to see under h0, and that's not very compatible. Our p-value is small, so we are going to reject the null. Reject h0 would be our decision. Our p-value is less than or equal to alpha, which is 5%. Would you say we're statistically significant? Yes or no? Are we statistically significant at a 5% level? Yes, because we rejected h0, because our p-value is small. And our conclusion would be then what? There is sufficient evidence to say what? To support a majority of patients in the population would improve using this treatment. Majority of all patients using this treatment would improve. Have we proven that you have a majority? Do we ever say that we've proven HA true or H not true? No. Beware of the word prove. Beware of the word probability in terms of confidence intervals. I have one more clicker question. It's our last one for today, so after this you can put it away. We still got a couple more slides to go through, but one clicker question regards this particular study. This would be how I would have a question on this new material that we've been doing and bring back chapter 3-4 ideas into the same question on an exam. We have a small sample size, and that's usually not great. Larger sample sizes are usually better. Although we were able to establish significance. Significance at a 5% level, but we would not be significant at a 1% level. But there is still some problems. Besides being a small sample, which is another fairly major issue regarding this particular study. Talk it over with your neighbor if you'd like. I'd like to see more correct answers than I am seeing. Oh, come on. What kind of study is it? Okay, observational study or experiment, right? Those are your choices. In an experiment, you actively impose the treatment on the subject. You take your subjects and you give them a treatment. Did we do that here? Yeah, we gave them a treatment and 9 of them improved. This was an experiment. It's not an observational study. Observational study, You simply ask a person, so have you taken vitamin C over the last month? Yes, you did. That's my treatment. You record. We gave them the treatment, these 9 people or 10 people in our study. It's an experiment. So now, process of elimination, you should be able to pick the right answer. We had 10 subjects in our study. 9 improved, 1 did not. They all responded. I know. Some people are still sleeping out there, or they're just being funny. It's response bias. In particular, how could you improve this study, this experiment? What is lacking in this study? Sample size is small, and I've already noted that as being a problem. That would be one acceptable. In fact, on the exam, I asked for 2 problems with the study, and one was small sample size in general, but we still reached a significant result. And the reason why we reached a significant result is because we have a response bias problem in the study. We gave everybody the treatment. 9 people improved. I'm not surprised that some people improve when you give them a treatment. Due to what effect? The placebo effect. We lack a control group in this study. I didn't have another group of patients that didn't get the treatment or got perhaps a dummy treatment if I could dummy it up. If I did, then I would be able to see the effect of the placebo and contrast that with the actual treated group to know what was more due to the treatment itself. We lack a control group would be the main issue here. Placebo effect is a type of response bias. All right. What do I have next? My pictures of the day. This is what I did this weekend. This is why I got no work done this weekend. I took, with 4 other adult leaders, 36 middle schoolers and high schoolers up for a retreat weekend up north, where we got to go tubing. That was a lot of fun. And giant ladder, caterpillar, that's very, very, very hard to do. I could not do it. Climbing the wall, and they all had a very good time. They all came back. No one was injured or hurt. Everyone was still smiling and sleeping on the way back. It was very successful overall. It's a lot of fun. Whew. All right. Page 91. We are close to the end of our material. We are going to finish today. Have you ever heard of those commercials, those studies, where they say 2 out of 3 dentists prefer this new Crest toothpaste? Do you ever wonder if they asked 3 dentists and 2 said they liked it? Or did they ask 300 and 200 said they liked it? That makes a difference. The sample size does play a role. We had a small sample design in this last study. Usually larger samples are better. They lead to smaller margin of errors when you're making your confidence interval. But you have to be a little careful. You do want to know what the sample size was to still evaluate that evidence coming in. If there really is an effect of this new treatment, it really would be helpful by a pretty moderate amount. If you don't have a large enough sample size, you might not detect it. You might not have significant results, even though there really is an effect and that new treatment is really better. Too small of a sample size can be an issue. Sometimes a pilot study done with a smaller sample sets the alpha level, significance level, at a higher level, so it allows for, if there is even some indication approaching significance, but maybe not quite there, let's still go on to that next level study and fund it some more. Then there's the other issue. With a very large sample, you're almost guaranteed a significant result, even if the actual size of the effect is very small and perhaps not really practically important. If there is any difference at all, even if it's really, really small, eventually you take enough data and you will see it, and you'll detect that difference. So this new production process, if it's put in place, should help your improving your output or reducing your defect rate. And you end up showing, yes, it would significantly reduce defects by that much. Now maybe that's important, but maybe not when you weigh that against, okay, if I go to this new process and I'll improve by this much and have to shut down my plant for a month and retrain all my workers and spend how much money to get that new process in place, maybe that's not worth it. So there's this issue of statistical significance, which is what the data says, versus practical importance. You've got to use your real-world knowledge and decide whether or not, even if you say statistically significant, are you going to go with that new theory or not? And beware then of those studies that are based on a huge sample size that have the headline, significant difference between men versus women in some rate. And you look at the difference and it's 44.2 and 44.3. Like, okay, that's significant. It is, because they had thousands and thousands of people in this long-term longitudinal study. So you need to look at the data too. Not just did we reject H naught or not, but I'd like to have the estimates, the p-hat, to be able to see actually how much of a difference was there and evaluate that from a practical view. So your p-value is helping you decide statistically significance. It does not tell you whether the effect size, the actual amount of improvement, is big or not. For that, you need the confidence interval. So when we said that the census rate seems to have changed, I would like to know, okay, so how much did it change by? I would like that difference of 44 to 48%, or that 44%, and make a confidence interval around that so I have an idea of how much different. Did it go down to 20% or did it go down to 44%? That's a big idea. So a test of hypotheses does not tell you necessarily what that actual size of the effect is. It just tells you that it was significantly different. The confidence interval tells you an idea of that size of the effect and a range of values for what that effect size could be. All right. Now, there are always mistakes that can happen. When you choose between two things, H naught or HA, one of them is true, one is not. You use your data and you pick one. You decide to go with one, and it could be wrong. There are two types of mistakes you can make then. You went with HA, this new theory, but H naught's really true. That's called a type 1 error. You stayed with H naught, but the alternative is really true. Type 2 error. Very clever names, I know. Type 1 error is rejecting H naught when H naught's true. Convicting an innocent person in the jury trial example. Type 2 error is staying with H naught, not rejecting it, when you should have gone with the new theory. That's saying a person is innocent when they really are guilty. There are consequences of both kinds of mistakes. Those consequences help to play a role at how you design the study that you're going to conduct. And in fact, the probability of making a type 1 error is your alpha. That significance level, it's not a very good alpha, is it? It looks like a whale or fish. Ugh. Alpha. That alpha significance level not only is setting that amount of evidence you need, how unusual do you need to be, but happens to be the chance that you would make a type 1 error before you look at the data. So you do want that to be a small, acceptable amount. And the type 2 error rate is called beta. We don't talk about beta as much. We actually talk about its complement more when we design studies. We don't talk about the chance of a type 2 error, but rather the power of the test. The power of the test is the complement of beta. A type 2 error is when you fail to reject H naught when HA is true. But what do we want to do when we're designing our test? I'm the researcher. I would like to show HA is true. The chance of rejecting H naught, going with HA when it is true, is the power of the test. The probability of rejecting H naught, which is what I would like to make as a decision, when I should, when HA is really true, is called the power of the test. You would like to design your test to be powerful, so that if that alternative theory of yours is correct, you will have a pretty good chance of choosing it. Power of the test then is the complement, because if HA is true, rejecting H naught is making the correct choice. Failing to reject is making that type 2 mistake. So whatever I can do to make beta small will make my power large. All right. Now one of your homework questions, it's question 8, the very last question, says you just did your whole test and you made your decision. And you will either write down that I rejected H naught in that problem or I didn't reject H naught. And you're asked, what kind of mistake could you have made? What's the name of the mistake that you could have made? So look at the definitions again. So if the decision is to reject H0, what's the only mistake you could have made? Type 1 error, because type 1 error only happens if you reject H0 when H0 is true. And if your decision is stay with H0, that's what you decide based on your data, then the only mistake you could have made is you chose the wrong one, and it would be called a type 2 error. When you make your decision, whatever that decision is, it's either right or wrong. You either made the right choice or you didn't. After you've made the decision, no more probability, no more chance. It's either right or wrong. But the deciding of setting up the protocol for how you're going to do the study and how much observations you're going to collect can be all set up, and you can establish alpha to be 5% and beta to be a certain level and figure out what sample size do I need so that I know my design of my study, my testing process will have these rates of accuracy or these rates of errors, and I can make them small. All right, couple of comments, and then one last simple example. I might go a little longer than usual today, but I'd rather finish and then have a clean start on Thursday. So, H0, status quo, prevailing viewpoint. We want to protect that. We don't want to go against that unless we're pretty sure that we should. So we're a little more concerned with alpha over beta. That's why all of the testing problems you see is take alpha to be 5%. Do it at a 10% significance level. We set alpha up front. Most of the tests that we're going through and describing with you, they will have the smallest beta for any given alpha that we decide to pick. So once you choose alpha, we're doing the test that would give you the best you can do on beta. Now there is an issue that for a fixed sample size, if you aren't changing your sample size, there's a trade-off between these alpha and beta rates. Alpha and beta move in opposite direction. There's a trade-off between alpha and beta. If you decide to let alpha go from 5% and decide, well, maybe I'll do the test without looking at your data yet at a 10% level, alpha goes up, you allow alpha to go up, then what happens with beta? It's going to go down. They're in opposite directions, trade-off. So if you're able to accept alpha to be up a little higher, you can let beta then get smaller. So there's a trade-off. Now ideally we want these probabilities of making mistakes small. You can't set them though equal to 0. If you decide alpha must be 0, I don't ever want to make a type 1 error, well then your decision every single time must be stay with H0, stay with H0. Never reject. And you'll never make a type 1 error, but then you never advance to any new theory. So you have to be willing to accept some small level. We have here that these probabilities we want to be small, but the issue here we're going to mention again is that, and you got it there, after you're done with the procedure and made your decision, no more probability. It's either right or wrong. All right, let's try it out. We've got a couple factors here to mention and then go through our example. What makes sense? Is a larger sample size better or a smaller sample size? What makes sense? Larger. Larger sample size, higher power. If you take more data from your population, and your population should have HA being true for it, you'll eventually show that and see that. What doesn't make as much logical sense, but it works, is that if you take a larger alpha, as we just discussed, alpha goes in the opposite direction as beta. So if alpha goes up, beta will come down. And if beta comes down, what happens to the power of the test, which is the complement of beta? Power, which is 1 minus beta, will go up. So if you have two researchers arguing about whether you should do it at a 5% level or a 10% level, the one that takes 10% actually ends up having a more powerful test in terms of the ability to detect that alternative if it were true. And then this one you really don't have much control over. You're testing whether the mean, let's say you're testing whether the proportion is 50% or more than 50%. What if the true proportion is really 51%? That is the truth. You take your data and you may not see that. What if it were 55%? No, I have a better chance of seeing that change, that difference. or if it were 60% or 80%, or in that last example we did, are we more than a majority? Do we have a majority? We had 90% in our sample. We saw that. The further from the null you are, the further your alternative is from the null, the higher the power. The more different I am from the null, the more likely I'll detect that difference. It's pretty basic, but you don't have the ability to do that. Now, the things you do have the ability to do is make sure your measurement process is accurate. If you have cholesterol levels and you have two different ways of measuring it, some are more accurate than others, and if you really want to have that accuracy and less variability, you'll see that difference better. But that's not always under the control. These first two are what you as a researcher can decide. All right, we have a simple example to finish out today. I have a basket of balls. There are 10 of them. Some of them are red, and some of them are white. I know there are 10, and the true model for that basket is either H0 or HA here. Either the basket has 9 red and 1 white, or it has 6 white with the 4 red. The prevailing viewpoint, these baskets before in the past have had the more red than white. But now I think things have changed, and I want to establish whether that's the case. You can, of course, select some data. 1 ball. I will allow you to take 1 ball at random from that basket, and with that one observation, you have to decide H0 or HA. So what's the most reasonable rule here? We're not going to calculate the p-value quite yet because we aren't going to look at the data yet, but the rule that makes sense here, just looking at the color of the ball that comes out, is what? Reject H0, go with HA if the ball turns out to be what? Does white make sense? I mean, if you got a red ball, you'd probably stay with H0. And if you got a white ball, that would be more leaning towards HA. All right, now the rule has been set. This is how I'm going to make my decision. I haven't done any data collecting yet, so I can talk about the chances of making mistakes. This is still before I look. Let's calculate the chance of a type 1 error. So, definition of a type 1 error is rejecting H0 when which one is true? When H0 is true. Rejecting H0 when it's true. All right, what does that mean in this problem here? That's the probability of seeing what color of ball? A white ball, because that leads to rejecting H0, when H0 is really true and the basket has 9 red and 1 white. So what's your probability of pulling out of that basket, the H0 basket, a white ball? 1 out of 10. If H0 really is true, and the basket has 9 red and 1 white, and I decide if it's white, I'm going to go against H0, I'll make a type 1 error about 10% of the time. Right? Okay, that's not too bad. That's an acceptable level for alpha that we've seen. How about the chance of a type 2 error? That's when you don't reject H0. You know, it's kind of a double negative. Fail to reject H0. But now you stay with H0, but you should have gone with HA because HA is true. But what does that mean in this problem? You reject H0 if the ball is white, so you're not going to reject H0 if the ball is red. And what's the chance of seeing a red ball when the population you're pulling that ball out of is the alternative one, the HA, 4 red with 6 white? How often will that happen? Getting a red ball from that HA model. It's just the proportion of balls in the basket that are red. %, that's beta. That's perhaps a little bit higher than I would like. But I'm only letting you take a sample of size 1. If you had a sample size 2 and had some rule laid out, you'd probably do better. What's the definition of power again? How does it relate to beta? Power is the complement of beta. So the power of my test is 60%. Most of the time you establish with your protocol that you lay out a test with like 90 or 95% power. We can only attain 60% level for power here. This is characteristics of this procedure. how you're going to make your decision. This testing of theories hypothesis procedure has these rates for how well it performs. All right, so now let's take our ball out of the basket. We pull the ball out of the basket and it is a white ball. If it is white, what is your decision? Do you reject H0 or fail to reject? You're going to reject H0 according to our rule. All right, you just rejected H0. Could you have made a mistake in choosing H0? Yeah, you could have. Could a mistake have been made? Yes. If so, which type? You rejected H0. You could have done that when H0 is really true, and that's called a type 1. What is the probability this type of mistake was made? What's the chance that I made a type 1 error? Careful. The chance you made a mistake, you already made the choice, so it's either wrong or right. The chance is not 10%. That is the property of the procedure. If you did this test over and over and H0 were really true, you'd make a type 1 error 10% of the time. But once you have pulled the ball out, looked at it, made your choice, you either picked the right theory or you didn't. 0 or 1 after you look. Key is it was already made, the decision. All right, we'll see you on Thursday. Thank you for your attention.